Right. Good evening, ladies and gentlemen of the internet. Hope you're doing well. Tonight, I want to walk you through on how to use Mississippi State SCoBi Simulator. So, assuming that you've downloaded everything from GitHub correctly, you should have this SCoBi folder up and ready for you to click on. So let's dive into that. Within here, you should see three different folders. The first one is the design folder, which contains the UML files that show the way that SCoBi decides how to run all of its different library functions and output its simulations to the user. So check that out if you're interested in that kind of thing. The docs folder contains the different manuals that we've created for the user to use. The one of interest for this presentation is the SCoBi User Manual, which is a nifty little guy, if I do say so myself. Today we're going to be going over section 2 of the document. No, I shouldn't do that. And we're just going to be going over some of the basics of operating the GUI and ways to think about setting up a simulation and that sort of thing. This is a nifty little document if you're wanting to get really quick clarification on different variables. We have almost every variable called out in the table of contents at the top. So if you're confused about something, you hopefully should just be able to click on it, or if not, feel free to send us an email and we'll try to update it so that we are a little bit more clear on things. This document is also really useful for setting up your Excel input configuration files. We've got a lot of tables that show you how to work with that. So definitely check this guy out once you're working with this sort of input. But alright, let's go to the third folder. I know it's a lot of folders, but we're getting towards the end of us talking about that right now. Here you should see the input, lib, and sims file. So you can kind of think about these three files as a sort of functional way of looking at things. So if I have a black box, let's say I have some sort of input file or input X, and it's going to go into a black box that's going to operate on that in a sort of f of x fashion and output things to a variable called y. In the same way, we have an input folder which has all of our x's, you could think, which then feed into the lib file or library folder and output things to the sims or simulations folders. So in this way we kind of operate things in a sort of a black box. So you don't really have to worry too much about the underlying physics and all that behind everything. It's just sort of taking care of you that way. I know I called the lib folder a black box. However, the main function is located within the very first part of the lib folder. So with that in mind, let's double click on this guy. I actually already have it open. So if you're interested, you can right click on this guy to hit run, and it'll open up the GUI right away. Alright, so before diving into this, it might be handy to keep a couple things in mind. While we're talking about this sort of thing, we suggest that you kind of have the sort of workflow like this in mind. Kind of have an idea of the simulation type that you're wanting to run. So if you're wanting to look at a forest, or if you're wanting to look at soil, or some different other kinds of vegetation canopy, kind of have an idea of what and how long and how many variables are going to go into that. Second, make your Excel inputs file. This is probably the most cumbersome aspect of this whole process, but hopefully we'll clear some of that up here soon. And finally, we're going to be going into the GUI inputs. Right. So for this presentation, we're going to be focusing on this guy right here of inputting things into the GUI, but we'll also be talking about how inputting things in the GUI affect your Excel inputs file. So let's hop into that guy. Okay, so again, this is your window for choosing between the different simulator options that we currently have. The ones on the four on the left are currently implemented, and the 4 on the right are things that we hope to implement in the future. So by that, we have the option to choose between the forest, agriculture, soil, surface soil moisture, and root zone soil moisture simulators. So let's just click on one of them. When you click on one of these, you're not necessarily committed to the action that you just did. If you go, oh no, I meant to click on agriculture, you still have that option within this window, as soon as you get into the GUI inputs right here. So let's get back to fault forest. All of the inputs that you see within these different sub-windows are essentially the same across all these different simulations. But it's the different options that are pre-configured into these different inputs that compose the differences between each of these different simulations. Okay, so the first submenu right here is the simulation settings submenu. Under campaign title, what this string essentially is for saving your simulation under a name that is somewhat useful to use. So let's just say that in August this year, you had some sort of tower experiment where you were looking at, I don't know, rice or something growing in a field, and you wanted to do some simulations on that with your signal opportunity transmitter. You wanted to change around some variables with your receiver to kind of get an idea of your reflectivities that you're going to be looking at. With this, your outputs and the simulations folder will be saved under a folder with this name, and this is all for your record keeping. This campaign title, this campaign parameter. Since I'm not too worried about that, we're going to change it back to default forest. Default forest corresponds to the default input configurations file that comes pre-configured with your SCoBi download. As you choose between the different simulation inputs, you'll see different input configuration files. And they're all for you to kind of get an idea of how to set up your own simulation with different variables. All right, so a minute ago I mentioned that Excel inputs files are probably the hardest part of setting this thing up. And there are, I believe, 3 parameters within this menu that will affect your Excel inputs file right off the bat. There's some options that take things away, but there are 3 that I think drastically change your inputs file. First is simulation mode, the second is ground cover, and the third, I believe, is going to be transmitter orientation right over here. Ground structure also changes things pretty significantly, and the antenna pattern affects a different file, but that's not necessarily something to worry about when you're starting out. So let me correct myself there. There are 4 parameters that really affect things. Again, that's simulation mode, ground cover, orientation, and ground structure. So for simulation mode, you have 2 options to choose from. You have snapshot, which is used if you have several different configurations for your transmitter and possibly your input file that you're wanting to change about, to just kind of get an idea of how a SOAP transmitter might interact with a given surface. A time series option is more for when you know some information maybe about the changing target that you're looking at. Maybe you know how the soil moisture is changing as a function of time. Maybe you know that your agriculture field is changing. Maybe you know that your the position of your transmitter is changing as a function of time. So with that, with this option, time series, you'd be able to input those changes within this Excel file that you can choose from right here. Okay, so under ground cover, you have the option between bare soil and vegetation. As you know, you'd kind of expect with bare soil, you're not worried about any forest or agricultural canopies that are going to be affecting your SOOP source, but with vegetation you are. And if you do select vegetation, that means within your Excel input file, your configuration inputs file, you're going to have to designate what your dielectric object is looking like. So with your vegetation, you have to represent that with a cylinder or a needle or a disc or of some sort, and those dimensions are changed within the configuration inputs file. All right, so next we have our preferences, which the first of is this include in master simulations. What this is sort of a record keeping sort of thing. Maybe you know that you have a particularly nasty simulation that's going to take several hours or maybe days to calculate, just because of how many variables that you're looking at. And if you want to make sure that this simulation is, marked out, SCoBi will create an Excel file that marks your important simulations that you're wanting to try to keep away from the rest. If you don't click this, all of your simulations will be placed into a folder called temporary within the simulations folders. Nothing wrong with that. It's just a different notation. By clicking this button right here, you can write your attenuations to an Excel file. And with all that, we can take a look at our transmitter. All right, so SCoBi stands for, as you know, Signal of Opportunity Coherent Bistatic Scattering Model. So this is where you start looking at the bistatic portion of this guy. So here we're going to be looking at the transmitter. Let's say that we have, let's say we have our Earth right here. And let's say we have our transmitter right here. It's this silly looking dipole. Alright, so first off, we have the frequency of our SOOP transmitter. I guess I can draw a receiver over here too. But anyway, so with this, we have the frequency of our transmitter listed in megahertz. So right here we have a P-band transmitter at 370 megahertz. The next option is the range to Earth center. So this specifies the distance of your transmitter from the center of the Earth out to here. So for this option, we have 42,164 kilometers. So it's way out in space. We're not looking at something that's on a tower. This is way out there. All right. So for the next one, the EIRP, or the effective isotropic radiated power, this variable denotes how much effective power you're outputting from your transmitter. So this is something that you would put in if you happen to know up front. Maybe you're looking at like a GPS transmitter, and you go look up and you know that, I can't quite remember, but maybe it's something like 20 decibels of power. I really can't remember. I remember it was like the amount of like a light bulb or something. which is definitely not 20 decibels if I'm mistaken. That's unitless anyway. Blah, 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 blah. The effective isotropic radiated power essentially functions like a sliding parameter. So if you know that your receive power is, if everything's set to 0, if everything's just 1 milliwatt that's transmitting, changing the effective isotropic radiated power is just going to shift your received power up by however many decibels that you put in here. So if you know that your received power is going to be minus 10 dB, then putting in 20 here would, minus 10 plus 20 is positive 10 dB for your received power. The polarization variable is pretty interesting. You have 4 options here. Right-hand circular polarized for R, L is left-hand circular polarized, X is, I believe, vertical, yeah, that's right, and Y is horizontal polarization. So to kind of get an idea of that, you can imagine a wave that's traveling in this sort of Z-hat direction. The Y-hat is going to be what's over what is parallel to the Earth's surface, and the X-hat is what's going to be perpendicular to the Earth's surface. So this is going to be vertically polarized, and this is going to denote horizontal polarization. All right, so for SCoBi, currently we are assuming that no matter how far away you are, the Earth's surface is flat. We're going to be hopefully changing this in updates of the model, but at the moment that is the underlying assumption for all of these. The orientation is the, it allows you to change the incidence and azimuth angle for your transmitter. If your transmitter is just going to be stuck in one position, you can just say that that is, geostationary, and input those values from the menu right here itself. However, if it changes, you'll have to type in variable, and that's when things will start affecting your Excel inputs file, like I hopefully mentioned earlier. All right, so that's 1, 2, 3 values that affect your configuration inputs file so far, but we'll get into that in a little bit. All right, let's look at our ground inputs. The dielectric model. We have 3 different options for calculating the dielectric of your soil. Dielectric of your soil. Yeah, I mean that's pretty much it. Just choose whatever model, Dobson, Mironov, and Wong, whichever is your preferred model for calculating your soil's relative permittivity and attenuation factor. Okay, for the ground structure, you have the option between single layered and multi-layered. So single layered is if you happen to know your penetration depth isn't very far with your transmitter, and you know that you can just represent that guy with just one block of some dielectric. Keeps things simple. Just use that if you can. However, if you're worried about your soil penetrating into the soil and that affecting your received signal, you'll need to click on this multi-layered guy right here. And that is going to, again, affect your Excel inputs file. And what SCoBi allows you to do is input the soil moistures, your known soil moisture values, as a function of the depth from the top of your surface. So let's say that you know that at 5 centimeters, what your soil moisture values are. You can input that into this Excel file. You can have an arbitrary number of those values, and after inputting your arbitrary number of soil moisture values, SCoBi allows you to use a fit function, 4 of which these are discrete slab, logistic regression, second order polynomial fit, and third order polynomial fit, to calculate a soil moisture profile based on those values. Okay, so for the receiver inputs, this is very similar to the transmitter inputs. The altitude is something that you want to use or be cautious of if you're interested in looking at the received power of your signal. If you're only interested in the reflectivity, this isn't something necessarily to worry about, but you know, as the signal propagates through the atmosphere and as free space path loss is affecting things, you might want to put your altitude over the Earth's surface with this variable here. The gain variable functions virtually identically to the effective isotropic radiated power for the transmitter input. What this guy does, again, is a sliding input value. So if you know that your received power is like in the minus 10 dB range, putting in 20, again, minus 10 plus 20, will shift that guy up to 10 decibels. Again, with polarization, you have the option to choose between these four values, which I just talked about. And the orientation, let's talk about that for a second. So let's say that things are fixed, and let's kind of draw things out here. So I have my transmitter right here, and I have my receiver right here. Well, that's a little close. And it has some beam pattern. I know this is not pretty, but regardless, and neither will this specular point be, but let's say that I have some specular point that looks something like this. It's going right through that main lobe. If you know your observation angle and your azimuth angle, you can have that guy fixed to that point. However, if you happen to know that your transmitter, this guy in red here, is going to be changing, and you're worried about your transmitter, let's just draw a second transmitter position here. Again, this is a little funny looking, but let's say that we have a second specular point that's going to be going through one of these side lobes right here. It's not really going to be hitting our main lobe. If you're worried about that, you can change your variable to be specular facing, so that instead of your main lobe being fixed, at each point you'll be pointing directly at the specular point of your transmitter. This is for a case where you're not really interested in the side lobes or antenna effects of your signal. Yeah, that's about it. Hopefully that makes some sense. All right, and finally for the antenna pattern input. So like I just drew here, if you know what your antenna input pattern is, you are more than welcome to define that. We are currently making functions to generate those from the CST technology suite if you're modeling your antenna in 3 dimensions. However, if you just want a really simple one, feel free to use the generalized Gaussian or cosine to the power n. If you have generalized Gaussian, you can define your half power beam width, currently 30 degrees right here, your side lobe level, your cross polarization level, and your pattern resolution, which defines the number of points for your pattern. So if I typed in 0.5 right here, the function for that would be for your theta values, and for your phi, you would have 180 degrees over n plus 1, and for this guy, you're going to have 260 degrees over n plus 1. So for n equals 0.5 right here, we're going to have $361 and $721. All right, and that covers the basics of your input right here. In our next videos, we're going to be going over running specific simulations and placing that into SCoBi. I guess one last thing that I should point out is that if you change any of these values that are different from the inputs, the default inputs, if you hit run SCoBi, if you try to run the simulator, you will be prompted to save your input configurations for record keeping within SCoBi. You have to do this to run the function, to run the simulator. And what that'll allow you to do is to load those inputs at some later date. And yeah, that's about it.